Right. Sure, absolutely. Okay, everybody. Welcome, welcome, welcome. So people, as you know, we are going to start this week for our remaining 2 weeks to do relativistic mechanics. And as you know, mechanics is the study of making things move. Now, up to this point, what we've been doing is look at things that are moving. And how they got to make move is something that we never discussed. It could be something that has a rocket pack on its back or something like that flying through space. In fact, we looked at spaceships floating around, these sorts of things. But at this point, everything that we did in our reference frames were always very passive. We just looked at things. Sure, every now and then the thing should have us send a light signal towards so you could actually see it or something like that. But in principle, everything that we've done is just being very passive, looking at things that move, and then view how much time does a certain process take as seen by one observer, how much distance is there in between two events, and seen by a different observer as well. So we could go from one set to another inertial frame to another inertial frame. But what if you start pushing against things? Now, question. How would you do this in classical, normal mechanics, non-relativistic mechanics? There's a mass floating around, you want to make it move differently than it was before.
Apply force.
You apply a force, exactly. So typically what you would do, this is still classical mechanics, non-relativistic, you would apply Newton's second law, agreed? So somebody tells you what the force is, somebody found out for you, if you are given this number or even this function, depending on circumstances, that you can calculate via this equation, then what the acceleration would be, how it would differ in its motion. Now that's fine enough. The person who gave us this nugget of insight was, of course, Newton in 1687. Question is, how does this change when you go to relativistic mechanics? Is there somebody who just by sheer accident happens to know what the answer is? If I would take this equation and I want to make it relativistic so that it fits with special relativity. Maybe it stays the same.
Would the mass become a relativistic mass?
Ah, that's okay. That's a nice idea, right? So the question is, if you have your law that tells you how things will accelerate given you start pushing against it with a certain force, and you know that this is the non-relativistic version, how can you change it to a relativistic version? And indeed, a natural suggestion will be, well, I might have read somewhere that masses become higher if a mass moves with a high velocity with respect to you, then mass goes up, yes? So then you would guess, this is wrong, sorry, but it is. You would guess, oh, well, it's something like this. Because now this part you can call relativistic mass.
Well, something happens with the acceleration, right? Because it's dv.
Yeah, so you
There you
just
go.
as a speed and time, and then you do something with the time because you know the time.
Of course. You can already sort of tell that just squeezing one gamma in between, because you think, well, maybe masses increase if you make if you start looking at masses that move with a certain velocity with respect to you, then some books, and certainly not me, tell you that masses will increase, and that therefore this gamma times this other thing, sometimes called the relativistic mass, should explain everything, and the rest should stay the same. But you very correctly point out, but no, wait a minute. There's also some timage going on here, yes? Mm-hmm. Because it's meter per second squared. So at the very least, the second squareds are ambiguous. Because whose seconds are those? Now that is not an issue in Newtonian physics, because everybody's time is everybody else's time. Not so much relativistic physics. If there's one thing you, of course, have seen many, many times over now, that the amount of time for one person is not the amount of time for another person. So the question immediately pops up. Well, whose acceleration is this, as seen by whose inertial frame? So one thing you can immediately tell, before even telling you what the actual formula is, one thing you can immediately tell, it's not going to be this one, because we want our formulas to hold in all inertial systems. If we're going to write this down, and we know that this formula will change from one inertial system to the next because of the delta t's in here somewhere in the A, then you know that this can apparently not hold for all inertial systems. So there might be one particular system where this is a correct, valid expression, but it's probably not going to be the same in other reference systems. So this is not it. Now I will tell you the answer first, okay? And then in the course of today and next week, we will see how we got there. There you go. That's it. Gamma to the third times m times a.
Oh, it makes sense.
Oh, it does? Okay, we don't need 2 lectures. It already makes sense. Why?
It's like probably weird, but like
Go ahead.
you need the gamma for the mass, and then you need 2 gammas for the 2 times that you
the
have in the acceleration,
yeah.
and you have 3 of them.
Yes.
It's kind of like here, but
Yeah, no, it's hand-wavingly, you're exactly correct. Now, just to repeat what he said, Ash said here a second ago, well, 1 gamma maybe has something to do with this idea that mass increases, but there's a meter per second squared, that is an acceleration, and the acceleration itself becomes with 2 gammas, because there's 2 times the time in there. Now, it's a little iffy, okay? Not because you said it, but it's a little iffy because, well, who gets gammas? That's question number 1. And secondly, there's also a distance in there. It's a dx over dt squared, and the dx itself also might come with a Lorentz thing. And, last iffy part, we already assumed that there should be at least 1 gamma because of the mass thing. And we never proved that. Where does that come from? So you can sort of already tell that this is probably right, and it is. But it's not, the hand-wavingly you can understand, but the whole idea is to get there. Now, this is going to take us 2 lectures. Yeah, I'm sorry, it's just the way that it is. So the way that I'm going to build this up is by 2 ways. Today I'm going to do everything except the introduction of forces. Okay? And once we have laid down how the mathematics for that works, then next week we're going to move on to introducing forces. And then ultimately we end up with this. So that's one part of mechanics. How do things move given you apply force to them? Secondly, energy and momentum. There is a property in classical mechanics, non-relativistic mechanics, about both energy and momentum.
Energy, the total amount of energy should be conserved, I guess, like...
That's it.
Right.
Energy is conserved. So that means that if you measure how much joules of energy is in a situation at a certain moment, and then you wait a couple of seconds or an hour or what have you, and then you measure again what the amount of energy is, the system might have changed. Things might have changed in between. But the amount of energy is going to be the same number. This is the conservation of energy. Now there's also conservation of momentum. And momentum, of course, has something to do with if you don't push against things, then that number should be the same. Those are classical concepts. Just out of curiosity, have you ever seen this being proven that these are constant, or is it just a factoid that was given on top of your rules of mechanics? So you have your mechanics, F equals m times a, and on top of that, by the way, momentum is conserved, energy is conserved.
Energy, but not...
You have seen the proof for the conservation of energy?
Long time ago.
Okay.
Isn't there a woman, I'm sorry, I don't really remember her name, but we've talked about it.
Okay, Amy Noether. Yes. Just
and she demonstrated it using Lagrangian.
Exactly. Exactly. Now I'm going to steal your comment for a moment. As you might know, I taught high school for a couple of years, and I had this book, and the book said in the chapter on energy, it says the law of conservative energy is nobody knows why this is true, but physicists have measured it so many times that they now believe that it is true. I was reading this with my classes, and it's, in the Me Too generation, this is very wrong. That you take one of the biggest discoveries in mathematical physics by a woman, And you write the book as if she never existed. I'm sure no one did that on purpose. But me in the class, we did actually, in real time, wrote the author of this book an email. I said, well, have you ever heard of Emmy Noether? And he sent an email back. He said, well, yes, but I'm not a theoretical physicist, so I didn't know about this exactly, such and such. Now, to give a sort of an historical anecdote about this, Emmy Noether indeed was a very brilliant mathematical physicist. In fact, Einstein called her the biggest mathematician since Euclid. And she was, well, these things are always debated, right? You have all these important mathematicians around. But the contribution that she made was enormous in a manner that I will explain in much more detail in the course of the next 2 lectures. I'm going to explain to you that there is a relationship between something that is called a symmetry. Now, what exactly that means in our context, we will get to, and a conservation law. Now, she found, just by mathematical means, that if you have a piece of nature and it obeys a certain symmetry, and again I will explain in detail what that means, then automatically you can point out what in that piece of nature is a conserved number. What numbers are not allowed to change. Not because you've measured it many times, you've never found an exception. No, because mathematics tells you that it should. This is called Noether's theorem. It is extremely powerful. It's so powerful that it underlies all of physics. Especially, let's take Jocko as an example again. Jocko constantly works with Noether's theorem because if there's one field in physics where you have all kinds of conserved numbers, it's particle physics. Charge, conserved number. Why is that so? Well, because we measured it. Yes, well, yes. Historically, we measured it, and then Noether showed that nature has no choice but to keep it constant. Baryon number, same thing. So there's well, if Jocko was here, he would object a little bit now. But energy, momentum, all these things, conserved numbers. Now, I will show you a mild version of Noether's theorem here. If you want to see a big version, I gave a series of lectures 2-3 years ago at Leiden University called The Physics of Energy, where I do the whole Noether theorem, but that it's just going through the mathematics takes 2 or 3 lectures or so. But if you, it's online somewhere, so you can view it if you want. I'm going to show you a mild version, only the part that we're going to need. But we're going to prove that it is the case. So by the end of today, I will have shown to you that the law of conservation of energy is a mathematical necessity of nature. There's nothing you can do about it. Same with the law of the conservation of momentum. I'm even going to make it such that I'm not going to specify what piece of nature. The way that I'm going to prove this is that you will find that this is true regardless of what piece of nature you happen to be looking at. So it's going to be the general proof of this theorem, yes? Now again, Noether proved that it was a much bigger theorem underneath that we now call the Noether theorem that comes with all kinds of extra information in there that we're just simply not going to need, and that itself is a whole series of lectures in itself. Now, going back to Noether, here's the historical thing again. The poor woman wasn't allowed to have a research position at the university. She lived around the turn of the century, 1800s, 1900s. She wasn't allowed to have a university position, yet she stayed. So she stayed there, got no money, got no salary. When she published, she had her male colleague publish the results. And ultimately later on in history, we found that it was her all along. And only after 20, what was it? We have to look in Wikipedia to find the exact details. But after 10, 15, 20 years or so, this is when she got her final position. Now, when I talked to my students back in high school about this, I actually mentioned this. I said, well, can you imagine that you go to a job every single day for 10 years? You don't get paid. Everything that you publish gets published under somebody else's name. Every single person will probably think, you know what, I'm not going to work anymore. I just go and do something else where I do actually get paid and get my recognition. Yet she stayed. If she had not done that, we would not have known about this theorem. So I always find Emmy Noether not just a testimonial of how strong mathematics is, but also how strong this particular individual was, that she stayed along for 10 years, not getting paid, just to give us this piece of physics. So I really want to give her some credit here when we're going to go through this.
The name, how is it spelled?
Oh, let me write it down. Emmy Noether. She was German. I think she was from Göttingen or something like that. Anyway, great person. Absolutely. Oh. So, again, going back to what we're going to do today, we're going to look at mechanics. I'm going to show you Noether's theorem in a mild form, and once we know how this works in general, then we're going to specify it for relativistic mechanics. Okay, that's the whole idea. Now, that gives us ultimately relativistic mechanics. But before I do that, I want to show you a quick and dirty way. So forget about Noether for a moment, we'll get to her in a moment. But let's do a quick and dirty way to get at least a piece of classical mechanics. And once we've seen what the rules are, then we're going to specify it more and go to, where's my marker? And then we're going to specify it to the general case. So here's the quick and dirty way. This is not my marker that I started with. It's not as inky as the, I literally just got a new package.
Yeah,
There's another one.
Check.
Sure.
Oh, it's my own stupid fault. Green cap, black marker, black cap. Okay. Oh yes. We have no idea how if you remember last Friday when there constantly was 5 markers without ink, this really is. Anyway, so here's the quick and dirty way to get the rules of relativistic mechanics. Okay. Now this rule you of course know by now. It's the Minkowski line element and it is invariant. Why is it invariant? Because nature has decided it to be invariant. This was our postulate all along. We got everything from here, so including all the Lorentz transforms in the time dilation, the Lorentz contractions, the relativistic time addition formula, the Minkowski space time diagrams, all of this came from here. I'm going to just mathematically play around with this thing for a while. Let's see what we end up with. How about, no physics involved, this is just mathematics. How about I do this? We all see what I did here? I divided away a d tau squared, the proper time squared. Now mathematicians don't like these sorts of things because what I did was I divided away a d tau squared. Then mathematically you end up with this and then I say, oh look, these are derivatives. Mathematicians don't like this sort of stuff because I treat the derivative as if it is a fraction. It isn't, but in physics it usually is. Oh, there's actually rules for this. So you can prove when it happens, when it is true and when it is not true, right? The derivative is not a fraction; it's a limit of a fraction. Yeah. So the real question that you have to ask yourself is, well, if you're going to divide this away and interpret this as derivatives, is that also true in the limit of infinitely small d tau? So in principle, you can make this a mathematical question and figure this out, and the answer is yes. To paraphrase one of the mathematical physics teachers at VU University. And when I was a student, he always said, well, we physicists, we first apply a mathematics rule wrong, and only if it gives us something that we want, then we go and check if it actually is allowed. And I do the same thing here. Long story short, this is allowed if you actually go through the mathematics. Now, this part, if you look at it, it just says amount of x direction distance divided by proper time, y amount of distance divided by proper time, z the amount, but it's all squared. So you can read this as just Pythagoras theorem of the x vector d tau squared minus. Do you see that this is true? So it's Pythagoras theorem. If you walk a certain amount in x direction, a certain amount in y direction, a certain amount in z direction, then you can also calculate how much you in total walked along the
hypotenuse.
Thank you. I was looking for that word. So you might as well just take the length of the vector itself. The vector x is shorthand for x, y, and z. Okay, this is just exactly the same thing, but just not specified in how much x, y, and z. All right. So we have here this. Still no physics done whatsoever. All just mathematics. Now I'm going to take the following step. Again, no mathematics, no physics, just mathematics. I'm going to multiply left and right by m squared, mass squared. Now, I hope you understand that there's absolutely no reason from mathematics not to do this. As long as the mass is not 0, well, even then it's allowed, but... Oh, I forgot an m. Yeah, there you go. Okay. Squared. And here's a squared as well. There you go. Okay. All right. Now, there is some physics in here, because we started with something that was invariant, right? Mm-hmm. This is the same formula in every inertia frame. It might be that this number is different, and this number is different, and that number is different from inertia frame to inertia frame, but the combination is always the same. When I multiply left and right by m, it might be that I've lost the invariance of the equation.
Just because of m?
Yes, because maybe m itself is not invariant. Maybe the amount of kilograms for one person is not the amount of kilograms for the next person. So, well, I hate to be impolite and ask somebody what that person's weight is, or unless you want to share.
70 kilos.
70 kilos. Okay, 70 kilos. In his inertia frame, 70 kilos. Now, I'm in a different inertia frame because he and I are moving with respect to each other, constant velocity. Suppose he was standing on a scale. Literally a scale machine in your bathroom that says with a little arrow what amount of kilograms it is. Would be 70 when he looks at it, right? Now, I look at the same scale and I look at what it says. What will it say for me?
70 also, probably.
Why won't it say 80? There's relativistic mass, isn't there?
Yeah, but if you look at the same, if you look at the number it's written.
Yes. Okay, but the number is just a representation of how strongly gravity is pulling you towards the Earth.
Yeah, but so what you will see will be the same, even if the measure isn't accurate. Maybe the measure isn't the same, but you will see the same number since it's an arrow written down.
I agree, but so the number will be the same. But do you think that the actual weight itself?
That may change, but
if that is the case, then according to me, the scale knowing that I'm looking at the thing would then all of a well, yeah, but how would the scale know that I'm looking towards you?
No, I mean, like for you, you can assume that the scale is off if whatever.
The scale is measuring
yes.
it in his inertial frame.
Yes, and the information comes towards me.
Yeah.
Okay.
So we have the same information that I do know.
Yes. So I would also see 70 kilos. Yes.
Yeah.
Now, of course, it might be blue shifted and red shifted somewhat. The information coming towards my way, but that's not the issue. The number itself does not change. But my point here is it's not so much just the information coming towards my eye that is still the same. The labeling of the 70 kilos. No, the actual physics is the same. I mean, the only way that it should not be 70 kilos, not the information coming towards my eye, but the actual amount of your weight, the only way that it should not give you 70 kilos is when, for some reason, the scale, or if you will, nature itself, knows that I'm observing you while I'm walking. Now, first of all, nature doesn't care about me walking around. It will not change your amount of kilos. Okay? Secondly, and that's a little thought experiment that I actually used with one of the tutorial groups last Friday. Suppose that he's sitting on a chair right now and the chair can only hold up to a certain amount of mass. The chair can only have 80 kilos before it cracks. Mm-hmm. Okay? Now, in his frame, your frame, 70 kilos, the chair says, I'm fine, I can hold you up. Now I start moving. If it were so that mass itself, not just a number on your scale, no, mass itself will increase. Do we have then we have a paradox, because if I run fast enough, your 70 will go to 75, 80
couldn't
something.
we think that the resistance of the chair will also change?
That is a very good point. That is your point as well. So everybody following this thought experiment. So if I run fast enough, I will come to both of your comments in a moment. If I run fast enough, then the idea that mass increases because of our relative velocity would mean that if I run fast enough, his 70 kilos in my frame would be 80, 90, 100, 200. The chair would break. Yes? Now that is a paradox. We see many paradoxes that turned out not to be real contradictions, as in, well, if you looked at it this way and you took into account that the other person looked at loss of simultaneity or something like that, then everything can be solved. You cannot solve an issue of a chair and a broken chair and an unbroken chair. Okay, there's nothing in the laws of relativity that says, well, but if you look at this way, then all of a sudden the chair reassembles itself back to its original state or something like that. This is a real paradox or a real contradiction. One that you cannot just play around with Lorentz transforms to make it work. Now both of you then came up with, oh, but wait. Maybe it's true that the amount of kilograms has indeed increased, but that the amount of force that the chair is able to hold him up has also increased with the same amount. That would solve the paradox, right?
Yep.
But here's the thing. Every single relativistic effect that we have looked at always happens in the direction of which you're walking. Lorentz contraction only happens in the direction of motion, of relative motion. Your chair holding you up is exactly perpendicular to that. That is completely unaffected by my motion. Your mass, being too much, right, if under the idea of relativistic mass, is a scalar. It doesn't have a direction at all. So that will actually change under the assumption of relativistic mass. That will change from inertial frame to inertial frame. But the amount of resistance that the chair can have should stay the same, because it's perpendicular to the direction of our relative motion. So we cannot solve this issue, this paradox, this actual contradiction, by saying, oh, but something happens with the resistance of the chair itself. The resistance happens here, all relativistic changes happen here. There's no way to solve this.
Yeah, but so the mass
But
isn't
Oh,
invariant.
really? That's right.
It would be logical. Like, I mean, the first thought would say like the mass is the same. Like, it maybe it's wrong, but like the most simple assumption, like
Is that it is the same?
yeah. But
Yes.
I don't see why you say that then it's no more invariant.
No.
just because
That was a
we
question that I
invented-
posed.
Oh,
I didn't say that I've made it
okay.
non-invariant. I said
It could
if
have been.
yes, when I start with something invariant, I multiplied everything with masses. If I want this to still be true in all inertial frames,
You have to prove
then
that mass is invariant.
I have to prove that mass is invariant. My thought experiment here is me trying to tell you that mass is invariant, right? Because if I don't make mass invariant, then I come with these actual contradictions of you sitting in your chair. There's another way of looking at this. I have at least two more ways, so I could spend an hour talking about this, about the idea of the non-existence of relativistic mass. Let me give you two short other ones. One slightly more involved than the other. Another reason why mass actually is an invariant. Mass, if you actually go to particle physics or quantum mechanics, mass is a combination of the actual inertia of the particles within an object. Like Vladimir, okay, so he's an object, he has many particles in there. His total amount of 70 kilos is a combination of how much inertia all of his individual particles have and their energies, how much they are holding on to each other. Now, if you go and ask Jacco and you ask him whether the strong nuclear force, the thing that actually holds the quarks together to make your protons, if that one cares about whether I'm walking around or not, he will say no. There's nothing in nuclear physics that tells you that masses, or if you will, the amount of interaction will change from one observer to another observer. Now, there's a reason to believe that mass is invariant coming from particle physics, and there's also one from general relativity. Now, that is it's slightly more involved, so I'll be very brief about that. General relativity, for the people who are going to follow this in period 5, is built upon a number of ideas. Well, one of the ideas is something that we call the weak equivalence principle. What does that mean? It simply means that things fall in the same way under gravity, always. So if you drop two things, they will fall with the same acceleration, and you know what that number is close to, at 9.81 meters second squared in absence of air friction and such. The fact that it's the same number for all masses, regardless of what you drop, is again called the weak equivalence principle. There's also a middle equivalence principle and a strong equivalence principle, but it's more and more involved. But let's stick to the weak one. The reason that happens is because mass has a dual role in physics. You might have heard this before from me or from somebody else. Mass tells you two things about an object. And I'm going to stick to your example. If you want, then we can switch to me. Okay, 85 kilos. Let's go. Okay, let's stick to you. 70 kilos. Mass tells you two things. One of them is how strongly gravity is pulling you towards another mass, because mass appears in Newton's gravitational law. A second interpretation of mass is inertia, how difficult it is to make a mass accelerate. That is the mass that you actually see here. You need, if you have more mass, you need more force to get the same acceleration. So if you will, the mass in this equation in your classical mechanics is what we call inertial mass. The resistance of masses to get into acceleration. And there's also this other thing, gravitational mass, that tells you how difficult or how strongly gravity is trying to pull this mass towards another thing. These are not the same physical ideas. You might think that they are the same because as a human being having, been here for 20 years or so, you're used to things that are difficult to pick up are also things that are difficult to push. But if you think about it for a little bit longer, there's absolutely no relationship between these two things. Take a mass, a big mass, say bowling ball, that's my prime example, and you hang it in empty space, extremely far away from any other masses, so that means the thing will feel no gravity. Okay? Give the thing a kick. You will still break your foot. Because the thing it's difficult to make the thing move. The thing resists itself against moving.
Isn't there a contradiction? If gravity is the same,
Yes.
like they fall with the same acceleration, though they have the same mass,
Yes.
isn't there a contradiction with like those two concepts? Like, because if it's two different objects with different mass and they do fall with the same
Yes.
speed, with the same acceleration, isn't there like
No.
problem?
I
I mean with the concepts.
I understand, but let me write down exactly why. Let's say that you're close to the Earth, the surface of the Earth. Then your high school physics tells you that the amount of mass, a gravity that you feel is this, yes, close to the Earth. Far away from the Earth, fine. You replace this by something like this, where m is the mass of the Earth and then g is 6 Newtonian constant is how far away you're from the center of the Earth.
Oh, it's just because it's an approximation.
No. There's nothing to do with approximations. Even if this is not the real law, because general relativity tells you that there is.
No, but I mean
Yes.
the fact that they fall with the same
Yes.
That's because the mass increases, but also the force increases.
Exactly.
They cancel out.
Let's put it in the terms of gravitational mass as inertial mass. This was the inertial mass. How difficult it is to get things into acceleration. So let's put a little I here. Yes. For inertial mass. This mass tells you how strongly gravity is pulling. So let's call that a little g. Gravitational mass. Now, if you want to calculate A, you just divide left and right. The acceleration that this mass will get due to this force is g over mi, big M over r squared, capital G. Agreed? Okay. For a reason that up to this day nobody knows why, these two numbers are represented by the same number. They have the same value.
Oh, okay. So but that is just like.
Exactly. You see that acceleration will come out the same regardless of what the mass was that you started with, because they drop out.
Yeah, if the initial mass is the same as
Exactly.
like gravity thing.
Exactly.
But we don't. It's just like that. Like there is no explanation.
We don't know why this is. It's one of the deepest mysteries of
Because
physics.
it's two different things. You know?
It's completely different. I mean, again, I can make a situation where I can feel an object's inertial mass. This is the bowling ball in space that I kick and I break my foot, even though it feels no gravity. So apparently you can make situations where one of the masses makes itself apparent and the other one does not. So you can really tell that there are different concepts. They do different things in physics. And the fact that they have the same number, or if you will, that they drop out, is up to this day a complete mystery. Nobody knows why this is true. But the fact that they do, by the way, this is not new that we know that it's true, because already Galileo in the 1500s already knew about this. He didn't know why, though. Newton also knew about this. He didn't know why. Einstein knew about this. He didn't know why. But the fact that it is true has an effect that the masses drop out altogether, because you can just remove them here. And as a result, the acceleration will be the same number for every mass that falls in the presence of the Earth. Sure, it depends on the mass of the Earth, that is still true, but the object that you actually drop will have the same acceleration. And by the way, if you actually put in the numbers here, mass of the Earth, 6 times 10 to the power 24 kilograms, G is 6, 7, 10 to the minus 11, the R is how far away you are from the center of the Earth, 6,400 kilometers. You do the math, you actually get 9.81 meter per second squared. So this is why that number is the same. So going back to my story, the weak equivalence principle, the idea that everything drops the same way, is equivalent to saying that inertial mass and gravitational mass are the same number. Again, nobody knows why this is true, but it's a building block of general relativity for reasons I cannot go into, because we have a lecture series about that in period 5. Okay, you cannot have general relativity without this principle. Yeah, I'm also plugging my course. So 5 December is your latest moment that you can hand in with your academic advisor what course you're going to do. Anyway, this is not the reason why I'm saying this. I'm saying this to make a point. Suppose that indeed mass would be not invariant. It would depend on how fast you're moving with respect to this. Which of the two masses does that correspond to? Right, we have two masses now. In principle, two different properties of an object. Inertial mass, gravitational mass. Suppose that one of them is indeed not invariant. Then the whole equivalence principle doesn't hold anymore, because the dropping out of these two numbers will not appear anymore. But that means that general relativity will not be true anymore, unless for that one particular inertial frame in which they happen to be the same number still. So if you introduce the idea of if relativistic mass, you throw out general relativity.
I don't see why if you have relativistic mass, you like reject both.
Which of these two do you think would be susceptible to a factor of gamma?
I don't have any idea. I'm just like, why does it only select one, like for example, and not the other? Why would it be only like 4? Why could it only influence like I don't know the inertial frame and not the gravity?
Well, let me reverse the question. Suppose that it would influence both masses.
Mm-hmm.
Why would it pick both masses if we already know that they're two different concepts?
The same, I don't know, for the same reason they are in the end they are the same, although they are different concepts. I mean, if it's possible in one way, why would it be possible? I don't know, like. Yeah, but it's I believe you. I mean.
No, I understand, but do you understand that what I'm making is only one assumption, right? These two numbers are the same. At the moment that you say, but they should stay the same in every inertial frame, then you're doing another assumption on top of that. You're building up assumptions. Now, I'm not saying that it is wrong. It could be that nation indeed puts a gamma in front of every one of them. It becomes more. It becomes less viewable. Now, ultimately, if the question is why is this true, we still don't know. Okay, so the best that I can give you are plausibility arguments. Although I do have to say the one with your chair pushing back, the pushing back force not being influenced by. Because it's perpendicular to the direction of motion, whereas your mass then would be, to me is very conclusive. Anyway, yes.
Okay, so in the first lecture, before we knew that C in the Minkowski line element was speed.
Yes.
Was
the speed of light. Yes.
And we just considered a speed. Isn't m squared c squared momentum squared?
It will be the momentum of what exactly? You're right. Momentum is mass times velocity, and here is a mass times velocity squared. Yeah. So you would think that it would be something like the momentum of light or something like that. Yes, it's the mass of light times the velocity of light. So it would be the mass of light.
It just looks very similar.
What is the mass of light?
Yeah, but no, exactly. Light has no mass.
But there is the momentum of the photon.
Yes, but what is the mass of the photon though?
Well, there's no mass.
Okay. Now, you can already tell that there is something momentum E going on here, yes?
Yeah.
Going back to the original idea here, I was going to give you a quick and dirty introduction to the laws of energy and momentum without Lagrangian mechanics, without Newton's theorem at this point. This is a quick and dirty way. In our narrative, what we were doing, we started with something that was invariant, did some math, and then I multiplied everything with m, and the only way to know that this is invariant, still invariant, is by knowing that m is still invariant. So I've multiplied everything with m, but because we now know, or very strongly suggest that m itself is still an invariant, this is still an invariant. And that means that whatever we're going to get out of here is still going to be the same for every single inertial frame. Now you're right, there is something momentum E going on here, and let's make that very explicit. I'm going to go for a different color now. Let's make things very explicit. My claim is, and I'm going to prove that this is the case, that this thing here is indeed momentum. Sure, momentum squared because of the square.
Yeah, well, if dx is a position or a position vector,
yes,
dx by dt would be the speed
Yes. I mean, you can already tell that this is going to happen, right? Here it says the amount of distance covered in an amount of time.
Yeah.
So that gives you velocity times n. That gives you momentum. But here's the rub. Because the amount of distance that you cover is measured in a person's frame, right? Some inertial frame. But the amount of time is the proper time. That is the amount of time measured by somebody for whom things do not move. So it's sort of a, this is not an official word, but I like to phrase it as such. It's sort of a bastard object. And not bastard as in negative, but you measure the amount of distance covered by any old inertial frame, because this holds for any inertial frame. But d tau is very specified. D tau is the amount of time for exactly one inertial frame. The inertial frame for which the two events happen at the same location. So let's make it explicit. Suppose that I'm happily moving about, and we're going to have two events. Event 1 is me standing here. Event 2 is me standing here. Okay? You are the x frame. And you're going to measure how long it takes for me to get from here to here, between the two events. Event 1, okay, 2 seconds. Okay? Your dt, not d tau, is 2 seconds. The amount of meters that I covered, I forget what it is, 3 meters or so? Let's say 3. So you have for these two events, the distance in space is 3 meters, the distance in time as measured by you is 2 seconds. So you would say my velocity is 2 meters or 3 meters divided by 2 seconds, 1.5 meters per second or so, yes? That is not this number. This number is how many meters you have seen me walk, 3 meters divided by the time measured by the guy who sees the events happen at the same location. Now, who is that guy? That is me, because I see event 1 happen in my position 0, and event 2 happens also in my position 0. There's an amount of time in between that we call d tau, and you know that d tau, whatever number it is not your number. It's not your whatever it was, 2 seconds. So it's if the two events were me standing here and me ending up here, then this number, this velocity, is how many meters you saw me walk in how much time I saw that it took me. This is what I say, bastard object. It's a little bit of both. So it's momentum, but it's not quite momentum, because if you would measure my momentum, you would take your amount of time and your amount of space to see these two events happen. So it's momentum-ish. Okay? Here something else happens. I will explain in a moment exactly how this works.
Is it correct to do that?
No. So no, exactly. What I'm saying is it's momentum-ish. It's momentum, so it's momentum-ish.
Okay.
Now, next claim. I will prove this in a moment, yeah? Next claim is that this number, this thing that you have here, and again I will show that this is the case, is going to be the energy over the speed of light and all of it squared. I will show why this is the case. All right? Remember, this is still the quick and dirty way. And if you're unhappy with this, then we do the neuter way, then you see that it is true. You have no choice. Now suppose that you agree with this. So let's just already call this P. It's a vector. Then you can already conclude from this that m squared c squared is going to be equal to E over c squared minus p squared. Assuming that you believe this, you end up here. And you fiddle around a little bit, you get this equation. Energy squared is momentum squared with some factors of c here and there plus mass squared.
Sorry, how did
Yes.
we get from the m squared c squared dt d tau squared to the E divided by c squared?
I haven't shown you yet.
Okay.
I'm making a claim now.
Okay, right.
And I will show you in a moment why this is true. But given that it is the case, and it is, you end up with this equation ultimately. Now, this is the correct equation that relates energy as measured by an observer to the momentum measured by the observer. More than that, it is invariant. Because we built it up from invariant thing, and every step in between was still invariant. So whatever you come up with here, this is going to be the correct equation for all observers. To be very clear, the amount of energy that one observer measures is different from the amount of energy that another observer measures.
Energy isn't invariant.
Exactly, energy is not invariant. Also, the momentum is not invariant. The amount of momentum that an object has is going to be different from one observer to another observer. So this number is going to be different between two observers. This number is, but this particular combination is always the same. This is very much the same as here. Our Minkowski line element already told you that if the amount of meters between two events as seen by one observer might be different than as seen by another observer, and the amount of time might be different, so this number and that number is different, but this combination is the same. What we now have is that a similar kind of numbers are different, but this combination is the same, also holds for energy and momentum in relativity. Again, under the assumption that this is true, yes? And I still have to show this to you. But before we do so, have people seen this equation before? I'm sure at the very least in particle physics, Jaco has flashed this thing many times over, I would say. And I wasn't there, but I'm guessing when he derived either the Klein-Gordon or the Dirac equation. Klein-Gordon, yeah. And then he probably used this and put them in some operators from quantum mechanics, and he ended up with the Klein-Gordon equation. That's exactly this. So what Jaco secretly was doing, I don't know if he emphasized this when he did it, was he built an equation for particles in quantum mechanics under the assumption that everybody in every inertial frame is allowed to use that equation. That's the Klein-Gordon equation.
Is that the Hamiltonian in the Klein-Gordon?
Yes.
Or in the Schrödinger's equation?
No, it's
the Klein-Gordon equation?
It's not for the Schrödinger. This will be the Hamiltonian for the Klein-Gordon equation.
Okay.
It's not for the Schrödinger equation because the Schrödinger equation, and again, the Schrödinger equation is a similar equation. Also tells you quantum mechanically how masses move, but on the assumption that things do not have to be invariant. So the Klein-Gordon equation is a step up from the Schrödinger one, just to make the connection to particle physics. So that's one comment. You might have seen this one before. Second comment is, you can play around with P, can't you? You can make momentum bigger and smaller depending on whether you start to move along with the thing that you're looking at. The particle flies along and you start to run along with it with exactly the same velocity as the particle.
Yeah.
Then the particle will have no momentum in your frame. Agreed? So that means you can, if you choose your coordinate frame, your reference frame correctly, can make this 0. This you can never make 0. There's no V's in there. It doesn't matter how fast you yourself are moving. Any time that you're going to measure a certain amount of energy of particles or masses, no matter how you choose your inertial frame, in other words, how you choose the P value to come out, you will always, at the very least, have this amount of energy.
So this is E equal to mc squared?
Yes, because if you move along with somebody, then P by definition is 0, and it says E equals mc squared. So already you can see this very famous formula, that the amount of energy that an object has is the mass times velocity squared, speed of light squared. But be very mindful of what I said here. Only under the condition that the object is in the same inertial frame as you. In other words, that you have the same momentum as the thing. Yes? Or that the thing has no momentum with respect to you.
So E equal to mc squared is only valid if you're moving at the speed of light?
No, it's only valid if you move along with the thing of which you're measuring the energy. The thing that you're looking at,
Yeah.
and you should have no relative velocity, so you should have the thing should have no momentum for you.
Okay.
So E is mc squared is always a nice party trick when somebody, I know physics, E is mc squared. Yes, but that statement is not invariant. There's exactly one inertial frame for which it holds. For any other one, it's this. Okay? This is the general rule. But the important thing here is that, again, this amount of energy is always there. So the amount of energy that you will find if you measure the energy of a moving object, the amount of energy that you will find is always going to be bigger or equal to mc squared. It's an amount of energy you can never get rid of, no matter how fast or slow you move with respect to the thing you're looking at. Yes?
What about the negative solution?
Did Jaco put you up to this?
He said something about it, but I don't think we reached the conclusion.
All right. Yeah. Okay. I will answer this very briefly. And for the people who are not following this, that's okay because but it is for particle physics. It is important because yes, if you look at this thing, it gives you the energy squared. And what you want to know is the energy. And you know that if you take the square root of an equation, you get plus or minus that square root. Yeah. So in principle, this equation doesn't just tell you plus 4 joules. It could also tell you minus 4 joules. And yes, it is related to antiparticles, but, and this is something I want to make very clear for the people who have done particle physics or want to do it in the future, the negative energies, or now let me rephrase, the negative energies are related to the particle antiparticles, the negative solutions, the mathematical negative solutions to this equation. But the energy of an antiparticle is not a negative number. And I really, I mean, I'm resisting myself to give you a lecture on how it does work, but I'll give you a very brief one. I cannot help myself, but I'll be very brief, okay? Now, the beautiful thing is if you do it in mathematics, but just in brief. If you would have a system where energies are allowed to be negative, then you run into a problem. Because that means as much as you can make particles have positive energy, the same amount you can also make particles have negative energy. If this thing gives you a plus 10, it also gives you minus 10. It gives you plus 1000, it also gives you minus 1000. Now, nature strives for lowest energy solutions. But if you see that the negative is just as much allowed as a positive, then that means that you can always create particles with negative energies. But that means if you have a configuration, say a particle, nucleus or something like that, then and that thing wants to have a negative amount of energy, or excuse me, a small amount of energy, you can make it as negative as you want. Now particles make the energies lower by sending out other particles. This is radioactivity, okay? But if you do not have a lower restriction on how low energies can become, then that means no particle is ever going to be stable. So if you take seriously the idea that for every plus value there should be an equivalent minus value, then that's equivalent to saying that no particle should ever be stable, and we know the particles are stable. If you don't believe that, just check yourself half an hour ago, okay? I mean, the world was still there. Long story short, that means that however you're going to physically interpret the negative energy solutions, you should not take them as actual energies. Now then Dirac came along, 1920s, Paul Dirac, and Dirac looked at this, and what Dirac originally did was say, you know what? Let me take one step back. Let me first say how other physicists thought. They thought, you know, you have a plus and minus solution, we just not look at the minus ones. This is not strange. I'm getting so sidetracked, but I love this stuff, okay? We have enough time for the other stuff. Here's in some coordinate frame, okay? Suppose that I were to throw up this pen, throw it up, let it drop down, and I ask you to calculate at what moment in time it will land at my feet. But I only start throwing it up from this height. It never started at my feet. Yeah. If you just do your classical high school mechanics, you will find two solutions. Because the force is m times g, right? And that means if you do the solving, you will find that the position is 1/2 times g times t squared. You solve for t, you get two t's. Yes. Mm-hmm. One in the future and one in the past. Yeah. We throw away the past solution. Why? Well, because it started at t0, and the pen will drop at my feet in the future. What does the -1 mean? It has a physical interpretation. Can you tell me what the negative solution means?
That it was.
Exactly. It's suppose that the pen had always been flying upward. When did it cross my hand, or when did it cross my feet? Well, that was some point hypothetically in the past. So mathematically, it gives you a solution that doesn't fit the boundary conditions. The situation was such that it started at my hand, but the equation doesn't know about this. Okay? So of course it gives me a negative time solution. So you, as the user of this mathematics, have to tell that mathematics, no, not the -1. The thing doesn't know that the pen started from your hand, so it gives you a minus solution, and you have to say, forget about the -1. It doesn't fit how I set up the problem. So we're perfectly willing in physics to throw away negative solutions if we don't like them, if it doesn't fit our boundaries, our system. Originally, people, when they looked at this and saw the negative ones, the negative energies, they thought, you know what? let's throw away the negative ones. But the difficulty was, but on what grounds exactly? Just the fact that nature is stable is surely great. The fact that you don't want particles to randomly, you want stable particles. But the Dirac came up with the idea, no. There's no reason from boundary conditions alone to tell you that the negatives ones should not be there. So what Dirac did was as follows. He said, suppose that you couple this particle, this system, with interaction with other particles. So he introduced the Maxwell field, plugging in, but period 4 electrodynamics. You have charged particles and you let them interact with an electromagnetic field around it. And then you write down the same stuff, but now the electromagnetic field in there as well. You get extra terms. And one of these extra terms tells you how much that particle is connecting to the electromagnetic field. And Dirac found that, okay, you get your negative energies, but what if we redefine these negative numbers as plus numbers? Would it still hold in the electromagnetic case? And the answer is yes, under the condition that you also flip the sign of the charge. So very hand-wavingly put, if you don't want the actual physical energies to be negative, you have to flip their sign. And the combination with electromagnetism tells you you're allowed to do that under the condition that you then also flip the sign of the charges. In this way you can make particles that are still stable because they still have positive amounts of energy, under the condition that their charges are flipped as well.
But those are antiparticles.
Exactly, but they are antiparticles with positive energy. So this is why I said that the negative solutions do have a relationship with antiparticles, but the antiparticles do not have negative energy. Anyway, that was my sidetrack. Long story short, quick and dirty way. Before I can do this in a couple of minutes, and then break. All of this is under the condition that I can show that this is energy, and I can show that this is momentum. Let's do that.
P stands for momentum, or is it like?
Yes, it's momentum.
Okay, no, P is not like a different thingy.
No, it's momentum. Small caveat is what we call relativistic momentum in a moment. But let's do the proof here. Let's start with the momentum one. Okay? So my claim is that dx over d tau is a form of momentum, momentum-ish. And we already saw it's momentum-ish. Why? Well, it's because it's a velocity or a distance divided by time, but, and we discussed this, it's somebody's distance divided by somebody else's time. Fortunately, we know exactly how to turn somebody else's time into somebody else's time. If we know that the two events happen for one of the two persons at the same location, we get time dilation. So we can actually turn my amount of time from walking from here to here into yours by just squeezing a gamma in front. And convince yourself that the gamma is at the right place, yes? My time gets the gamma because the two things happen for me at the same location. So I've now replaced my time by your time.
Yeah, it gets the gamma, but you have to like switch it in the equation. So it's 1 over, no?
Yes, thank you. Yes. I'm very sorry. Yes, you're right. D tau is
yeah, the property.
is 1 over gamma dt. That's it. Now this, we now have gamma times mv, and now this is an actual v. Do you see this? It's your amount of distance divided by your amount of time. So that's actually how fast you would see me move. And this part is in Newtonian physics what you call momentum, m times v. So what we have here is, if you will, these were all vectors. What you have here is Newtonian momentum. This is why I put this subscript n, Newtonian, times gamma. This thing is what we call relativistic momentum. So this thing, by definition, so let me triple equality sign. By definition, we call this relativistic momentum. It's Newtonian momentum times gamma.
Is the m, so is for a relativistic mass, is it not m is equal to gamma into the rest mass, so m0?
Yes, this is where the whole idea of relativistic mass comes from. That people say, oh, you have an m, you have a gamma, you might as well call that one relativistic mass.
Yeah.
And if you're very clear that is what you mean, I'm happy with it, because then you can say, oh, you know what, this is relativistic mass times velocity. And you get also to relativistic momentum.
But in this case, gamma m and then the velocity vector m is the rest mass?
Yes, this every m that I write is rest mass. I'm never going to talk about relativistic mass. In principle, if you really, really want, you can replace every gamma times m and you call it relativistic mass. And that in principle, as a mathematical tool, that's fine. But never, ever
As a physical.
see it as a physical constant. This is your scale all of a sudden saying 80 just because I happen to be walking with respect to you. So it's a nice bookkeeping tool maybe, but it has no bearing on actual measurable physics. Now, long story short, we call this relativistic momentum. So this is momentum-ish, okay? So it's a strange concept. It's taking somebody's momentum and multiplying it by gamma. Whenever I'm not going to write a subscript, I will always mean from now on relativistic momentum. Gamma times the Newtonian one. This is the standard in relativity. Nobody talks about Newtonian momenta. You can do one thing though, because you know that gamma is 1 over v over c squared square root. This is Newtonian momentum, yeah, still writing the same thing. Now suppose that you're looking at something that is not very quickly moving with respect to you. So the thing that you're measuring the momentum of, v, is small with respect to c. What happens to this thing?
It's very close to 1.
Exactly. So if the thing that you're looking at is very slow compared to you, there's no difference that you can measure between relativistic and Newtonian momentum. So what I meant here when I wrote momentum, I meant relativistic momentum. Nice thing is, it's really just your momentum that you already knew. It actually boils down to the same thing if things are not moving too fast, but you already knew the same things happen in relativity if you go faster. And the only claim that I'm making now is you have to replace your momentum, Newtonian, by this gamma times Newtonian momentum. I have not shown that it's conserved though. Because now you can ask the question, well, is this one conserved? Or is this one conserved in time? It's the full thing. And the reason that your high school physics teacher always said that this one is conserved is because at small velocities there is no difference between the two. This one is conserved, this one is not. Are they invariant, either of them?
No. If we just go back to the formula, by themselves and not invariant.
Sure, but that's true. Both, none of them, the Newtonian one is not invariant, and the relativist, thank you, the relativistic one. And you already knew this, right? The invariant means that the same number should come out regardless how fast you yourself are moving, but the
if
thing
we
that
move at the same speed as the ball, for example.
of course, I mean, if you move along with the thing, that the thing will have no. So even without relativity, already in classical mechanics, momentum was never invariant, and it still isn't. Now, that solves this thing. This one is a little bit more tricky, but we'll get there. My claim was that E over C, excuse me, that mc times dt d tau is the same as energy divided by c. Let's see if that is the case. Now, this doesn't mean, here we have the luxury that at the very least it looked momentum-ish, right? Because it had, at least was a distance divided by time times an m. But now we don't have this luxury, so we have to do a little more to show that this is an energy. Well, first of all, you can look at the units if you want. Because energy is, if you look at the units, well, it's joules, but it's the same as kilogram times meter times seconds. It's newtons times meter. And Newton itself is kilogram times meter divided by second squared. So it will be kilogram times meter squared divided by second squared. Up to a factor of c, that's exactly what you have here. So it looks energy-ish, at least in units. But we can do a little better, because dt over d tau, do we happen to know an expression for this?
dt over d tau, we can just say exactly the same thing we did with
It's time dilation. So, if you will, this is just mc over c times 1 minus v over c squared. Now,
Everything is squared, no? Sure.
this is correct.
Squared.
Yeah.
Why should they, why
No,
would it
I'm
be
just
square?
like, you just took like the, because like if we took the formula,
But it's just because it's good.
it's just like,
He's just showing the inside.
Yeah,
not
yeah,
the 32.
So, is it about this square? That one?
yeah, yeah.
Okay, no, but I want to look at the thing inside. So my claim is this is E over C. Energy over C. Okay. Now, well, I mean, if you multiply all of this by C, it does indeed give you a kilogram times meter squared second squared, and that is by definition a joule. So it has the energy, the unit of an energy. But things having the same unit does not make it an energy. Again, classical mechanics of torque, the amount of how much you have to push against things to make things move, is also in Dutch people, krachtmalarm. It's a force times how far from the turning point it is. That also has the dimension of energy, but it's a completely different thing. So that is not enough reason. But here's the beautiful thing. Let's do the same trick as we did here. Suppose that you look at a mass that has a low velocity with respect to you. Do you remember that we had this trick how to,
oh yeah.
Binomial approximation.
yeah, or first order Taylor approximation, whatever you want to call it, but you remember this, yes?
Yeah.
1 plus x to the n is the same as 1 plus nx, on the condition that nx is very small. Well, we have the thing here. We have 1 minus v over c squared to the power minus 1/2. So by good approximation, under the condition that v over c is small, this is the same as 1 minus v over c squared times minus 1/2. No, excuse me. Taylor approximation. So if you look at things that are not moving too fast, this thing, whatever it is, will look like this. This is what you will measure.
Sorry, why is there a c squared?
Because it was here already.
No, it's like it's energy divided by C, and it's
Yeah.
equal to C as
So
just the energy.
I was originally looking at E over C. Yeah, E over C.
But you square rooted everything from mc dt.
No, I took this expression, took its square root, that gave me E over C,
And then you multiply.
and then I multiplied everything by C. Yeah, Robin, what I did was this. I said this whole thing is this whole thing.
Yeah.
So without the squares, E over C is everything here without the squares.
Yeah.
And if you just want to have E, then I multiply everything with C.
Okay.
It gives you this. It gives you, going through the brackets, mc squared plus,
Shouldn't it be divided though by the approximation?
sorry?
Shouldn't it be divided by the approximation?
No, this is fully correct.
Because he multiplies with minus half. of
Minus
the
1/2.
square.
Yes.
Right.
This square root, no, I understand what you mean.
Oh,
But this 1 over square root is the same as
absolutely.
this whole thing to the power minus 1/2.
Absolutely.
Low velocities give you this. Now let that sink in for a moment. What does that? At the very least, a second term. Does it sound
Kinetic
too
energy.
familiar?
Kinetic energy.
Kinetic energy. So apparently, whatever this thing is, I already gave away that it's energy, but whatever this thing is, if you make it Newtonian, it just gives you the kinetic energy of the thing. It's exactly what you would expect if you would measure something that floats by you with velocity v. It should have an energy mv squared, 1/2 mv squared. That's what you get.
Plus mc squared.
Yeah, but it's the mc. Yeah, that's true. You get also this part. But even if you didn't know about relativity, there's a reason not to be bothered too much in Newtonian physics about mc squared. This
Is
part.
that what you said earlier, that the mass is 0 of light?
No, because this is not for light. This is whatever floats by.
So in this case, c is not the speed of light.
It is the speed of light because it was always the speed of light where it was built in.
Okay.
But we're not looking at something that is light. We're looking at a mass floating by, whatever the mass is. So the C is not there because the thing that we're looking at is light. The C is there because it was already in from the outset. Now, back to my question. We all see that whatever this is, if you go to low velocities, it gives you exactly the energy as you would measure in Newtonian theory. it gives you an extra term. And you say, oh look, I use MC squared. Yes, but forget about that, you already knew this. My claim is this part has absolutely no physical meaning in Newtonian physics. You might know this from high school, you might know this from your classical mechanics course maybe. This thing you might as well drop it altogether. Might as well be 0. Or you know what? Might as well add 1 million to this.
Because the speed of light is not invariant.
Has nothing to do with relativity or the speed of light. It's just classical mechanics. So my point is you can add whatever number to this expression, constant number. It has absolutely no bearing on what you're going to measure.
Yeah, because what we are looking is like a constant, not an invariant. So whatever it doesn't matter if we add a constant. It's what was important is that it stays the same over time, not depending on the referential.
That is a good point, but now you're already assuming that's going to be constant. We haven't proven it yet.
Is that just the potential energy and then it's minus, like it will be the same as kinetic energy?
Okay, great. This is what Ryan, was that your point?
I was going to say we're always looking at energy difference.
Exactly. The only thing that matters in physics, the only thing that you can measure is the energy difference. This, by the way, is your point. Because the force, Newtonian force, is literally 1/2 times the change in potential energy. So whatever you add to your energy, it will drop out if you take differences. So this thing has absolutely no physical meaning whatsoever in Newtonian physics. So knowing that we can add or subtract constant amounts of energy at will, it doesn't change your physics in the slightest. That means that you might as well not look at this thing, and then you get exactly what I promised that it would be, that this thing is the energy as you would measure in Newtonian physics.
Is it different? So in relativistic, then what will that term?
Yes. Now, I'm going to. So when I went from here to here, I made it Newtonian. Yes, I looked at things that are moving very slowly. But we already saw here that the MC squared part in relativistic physics actually does have a meaning, because that's enough energy that you will always end up with that you cannot get away from. So from here to here, from relativistic to Newtonian, this doesn't matter anymore. But sticking here, then the MC squared does have a meaning. Now, long story short, my claim was that this thing is energy over c. And you can tell just by looking at the Newtonian case that it should be. This thing is momentum. If you on momentum-ish, it's the relativistic momentum. And under that condition, this holds, and you have your relationship between energy and momentum in relativity. And yes, it is invariant. Yes?
Sorry, just the Newtonian momentum, where does actually have 4 components or 3 components?
This has 3. And yes, again for the particle physicist or the one person in the room already did general relativity last year, you can also, if you're not picking this up, don't worry about it. But this energy and this new relativistic momentum together go, and we call this a 4 vector. Anyway, if you have no idea what to talk about, the last part is not important. No, not for now. Now, long story short, quick and dirty way, and now have your energy momentum relationship. What I have not shown, then time for a break, but what I have not shown is that this number, this energy that we now know is an energy, is conserved. We know it's not an invariant. The amount of energy changes from one person to the next. But within one frame it is a conserved number, but that does not show from this derivation. The only thing that this derivation shows is how this thing and that thing are related. So that means after break, Newtonian mechanics, and then I will show you how that they're also constant. Okay, break for you, coffee for me. People, let's see, we have 20 minutes left, the Lagrangian part. The question is, should I be moving very fast with my blackboard to make sure that I can fit everything on there in the amount of time, or should you be moving? Question is, whose time dilation do we need to apply in order to make sure that everything will fit in 20 minutes?
I think you should be moving very fast.
No, we have to move.
That's fine.
So its time is lower and...
Okay, you know what, let me at least write very fast, okay? people. So as a small summary of what we did before the break, we had a quick and dirty way. We started with the Minkowski line element. You know, it's invariant. We played around with just algebra. We never actually put any new physics in. The only physical step that we did was convince ourselves that the mass that we multiplied everything with was itself an invariant. And as a second step, that whatever we got out, there was a relationship between all these things, that we can actually interpret these things as momenta and energies. What I have not proven is that the energy is a constant, conserved, or that Newtonian, relativistic and or Newtonian momentum is conserved. That I have not proven. But I do have to say that during the break there was a person, and in beautiful sequel to the Amy story, it was a female person who actually already proved Newton's second law that I started with, that I was going to prove to you next week. Is it okay if I mention names?
Shania.
Exactly, Shania came up with this. Remember that I said that in that the Newtonian version F is m times a, that doesn't hold, not even if you squeeze a gamma in front, because you think something about masses being invariant and such. She came up with a very good idea. Because remember that we had our momentum, this thing, and our relativistic momentum, and she came up with a brilliant and beautifully correct interpretation that force you can define as mass times acceleration. But again, this is not an invariant statement, but in Newtonian physics, this is equal to the change of the momentum in time. That's the same statement. And then she realized, but wait a minute, the F equals m times a might not be invariant, but we do know something about p's in relativistic mechanics, yes? We know that p should not be Newtonian p, it should be this p. My claim is, and you can easily prove this for yourself, and otherwise you have to wait until next week when I'm going to show it in a different way, that if you take this thing, squeeze it in there, you will get your gamma to the third m times a. So there's your proof. That is the, again, quick and dirty way, but you're in the filling Amy Noether's shoes. I hope that if you get a job, you get paid, as opposed to that lady back in the day. Now let's do the a more formal way, yes? Again, right now I'm just going to look at things that themselves do not feel forces. So, but I'm going to show you this in the Lagrangian way. Now I am aware that Lagrangian mechanics is taught for 1 week in the classical mechanics course, but that hardly does it justice. That's not a statement about the lecturer or the lecture series. It's just simply a statement about the beauty of the theory. Just out of interest, who has seen Lagrangian mechanics before in any context? That is almost everybody. Okay. Now, then, at the very least, we can very briefly go through how it works. Now, Lagrangian mechanics, so consider this an intermezzo, just to show you how the methodology works, and then we're going to apply to relativistic physics, okay? Now, the methodology of Lagrangian mechanics, so here's your intermezzo. The methodology is as follows. Somebody gives you a Lagrangian. Now, what the hell is a Lagrangian? Well, a Lagrangian, you might have heard before, is kinetic energy minus potential energy. You don't even have to specify that. It's a function. You look at something that happens in nature. Now, things that happen in nature happen at a certain location in time and with a certain velocity in time. Try to give me any example of something happening in nature that does not depend either on velocity or on position. Could be light, could be thermodynamics, could be biology, could be whatever. So, what I've written down now is a very general statement. I'm just saying there is a piece of nature and you can describe by this crazy function that we call Lagrangian, and the Lagrangian will depend on where things are that you're looking at and with what velocity they are moving. This is very abstract. Do you agree? It's a function that depends on place and velocity. I'm going to make it more abstract. Out of this function, you can make another function. You take this thing, this Lagrangian thing, and you integrate it over time. You get a new thing. This new thing is called the action. And this is the Lagrangian. Now, just from mathematics alone, you can tell that this is a number. Agreed? It's not a function. This is a function. For every moment in time, it gives you a different number. But because you're integrating over time, and integration, as you know, just means take every number in between here and here for the time. You get different values for what comes out of L, different numbers, and you add all these numbers together. What you will get out is a number. That number is 17. Or, you know, might always also be -4. You know, it might also be infinity. Or it could be pi to the power e. The point is, it's a number. It's not a function anymore. Now, up to this point, this is not physics. This is me just saying that there are functions that we call Lagrangians. Depends on where the thing is that you're looking at and how fast it is moving. You can take that Lagrangian, turn it into a number. We call that thing the action. Not physics, just mathematical statements. Here's the physics part. It's called the principle of minimal action. What is this principle? This is where the physics comes in. Nature makes choices. If you look at a piece of thing moving, again, it could be some mass, it could be a biological system, it could be me walking through this lecture room. Anything that can be written as such a thing gives you a number for this. Now, multiple numbers could come out. Could be 17, could be -4. And what the number is that comes out depends on how the thing has moved and how fast it has moved. Do you see that if something has moved in a different way, its position at the moment in time was different than for the other thing that moved, then this number that comes out is going to be a different number. So let's make it explicit. I'm going to throw this pen around. Not in real life, but suppose I throw this pen around, okay? If I throw it in that direction, it will have a different x as a function of t and a different function of v of t than if I would have thrown it, suppose, straight upward or so. Different numbers will come out. Now suppose that I throw it in this direction. Then the question is, okay, what path does it follow through space? What is x as a function of time? What is v as a function of time? In Newtonian physics, you know how to solve this in principle, yes? F equals m times a. You know what the F is? It's gravity and how much I pushed it around and such and how much friction there is. In principle, it might be difficult, but in principle you can calculate where it will land at what point in time. You know how it flew through space. You know the function xt. Now suppose that I don't know what that function is. I don't know how the thing flew in space. It might have flown this way, it might have flown a little bit that way. I don't know what it is because I'm not smart enough to solve Newtonian physics. Then the principle of minimal action says, well, calculate what number comes out if it flew this way. Calculate what number comes out if it flew that way. You get different numbers, 17 and -4. Nature will make the thing flow through space in such a way that the number is smallest. So if I have two options, 4 and 17, nature will choose 4 and not 17. That's a very abstract statement, isn't it? It's as if I throw the pen around, nature then calculates all the possible ways it could have flown, then that's in principle an infinite amount, then looks at all these numbers and says, oh look, that's the one with the smallest number, that's the one I'm actually going to let the pen follow through space. How would nature know this? This is what nature does. It's called the principle of minimal action, and it's highly abstract. You agree with me, yes?
Mm-hmm. So, for example, if you just were blindfolded, you throw your pen whatever place, and we have to guess beforehand where your pen will fall.
Yes.
Then how is it possible?
I will give you an answer in a moment. There you go. This is the principle of minimal action. Again, I will get to you in a moment. This is possibly one of the most important statements in all of physics, because we found that all physics agrees with this law. No exception has been found. Now you can ask, okay, but why does nature do this? And there is actually an answer, but it comes from quantum mechanics. Very briefly, because as you know, I love tangents and such. Very briefly, you know that in quantum mechanics, if you throw a pen, it doesn't strictly follow that path, yes? It might also follow the path next to it and one of the other paths. In principle, there's a certainty in nature that tells you it could have flown this way, could have flown that way. Ultimately, it will only follow one path, but every of these paths comes with a Schrödinger, or more involved, with a Klein-Gordon maybe, wave function. And you have to take the modulo square of that wave function to tell you how it actually flew, or what the possibility is that it flew in that direction. Now suppose that you would throw this pen around and it would follow this path. That comes with a Schrödinger function. But this path comes with a different Schrödinger function, and these overlap. And if you then calculate where the Schrödinger functions overlap constructively the most, so where the possibility is the biggest that it will flow that particular path, that's equivalent to stating that this is true. So it's really a quantum mechanical statement. Now, we're not going to delve into this. This is just going to be a fact. But I'm just going to... The reason that I mentioned this is because it is really what nature does, and it's not just by assumption or by testing. We can prove this by quantum mechanics. Now, this is highly abstract, because what I tell you is, well, somebody gives you a Lagrangian, how nature is in this classroom before I throw the pen around, and then this tells you what path is actually chosen. Highly abstract. Because where do you get your Lagrangian from? Who tells you what this particular function of x and v should be? Where does that come from? Now, is this very different from Newtonian physics? Suppose that you don't really don't want to work with Lagrangian physics. You want to do Newtonian physics. Where do you get your F from? Dutch people say Binas. Because Binas told me so, or my teacher told me so.
The situation, I guess.
Yes, I mean, but given a situation, yes. But given a situation, suppose I throw this pen around and I want to know what the F was on which the pen flies. Then at the very least should be gravity, agreed? Newtonian gravity. And then you say, okay, but where do I get that particular version of F from? M times n divided by r squared. Then you say, well, Newtonian found it at some point. Now, we are so ridiculously used to already knowing a catalog of possible forces by heart. In this situation, the F has this particular form. In that situation, it should be that. And if it's friction, then it should be going with v squared. Or it's a pendulum, it should be something that goes inversely proportional to the position. We are so used that we have a catalog in our head of different Fs for different situations that we hardly even think about that it's highly abstract that somebody gave you an F for a situation and from that point on you calculate how things move.
Normally it's the opposite.
How's that?
You see the thing moving and you want to find it.
Yes, but then at the very least you still have to question where does this come from in the first place, the equation. My point here is that what we have in Newtonian physics is you have a rule, and in that rule you have to substitute the situation that you're looking at. The rule is Newton's second law, and the thing that you have to substitute to specify your situation is your F. Nobody tells you where the F comes from, except for much testing in the laboratory. Nobody told you where this rule came from in the first place. I have the same thing here. I have a rule, and something I have to substitute in the rule. It's the same amount of assumptions. It is the same amount of physics. It's the same amount of I have no idea where this comes from. Okay? The reason that we prefer this one, both in our educational system and as human beings, and also history, because this was the first one that was found by Newton in 1687, is simply because this agrees with intuition. If you push against something, it will start to accelerate. So, you know, my cat knows how that works. Right? My cat knows how to open a door. She hangs herself from the door handle and then it opens. She figured that out at some point. So my cat has some natural intuition for this thing just by having played as a kitten. Now you have also a natural intuition for this one. So naturally, when people started thinking about these things for the first time, this is the version that it came up with. Lagrange, the person, the scientist, found, wait a minute, you can replace this rule by this rule. You can replace this abstract function coming from nowhere by this abstract function from nowhere and get the same physics out. So all of this is just me trying to give you the feeling that this might sound very abstract to you, but it's only because this is just as abstract, but you're very much used to this one. That's the only difference. It's the same amount of assumption, it's the same amount of physics. Now, why do we use this one in theoretical physics exclusively? In physics, theoretical physics, nobody works with Newtonian mechanics. Now, most of you, up to 2 people I think, said that you have seen Lagrangian mechanics before. do you know why, from your experience in Lagrangian physics, why this one is preferred over this one?
Is it because energy in general can always be expressed somehow in terms of the position with respect to time and the velocity with respect?
But I see no energies here.
I mean, the
So it's a Lagrangian.
potential minus kind of.
But I mean, I understand your intuition,
Yeah.
but I haven't said anything about energy here.
No.
There's no energy. There's just a function.
Just because mathematically it's easier to couple some stuff with
Well, that depends on the situation. There are situations where this gets you is easier and this one is not. That's situation dependent. But maybe you have an idea.
I don't know. I mean, I remember from classical mechanics that Lagrangian really doesn't require much intuition in it. Like, it's
Yes.
what Ronald used to say is you can plug it in a computer and he will calculate the number.
Okay, so for Ronald probably said it's for pragmatic reasons.
Yeah.
It's easier. For computers, it's easier to work with this than with that.
Yeah.
That is of course true.
If
Yes.
it's more abstract in a way, it's also a more powerful tool, I guess. Like you can apply it to way more things
Yes.
than just the force, because in terms of force you need to find equilibrate, know every force and so on, which in reality is often not the case. We also
Yes.
so I guess the fact that this might be more abstract can be applied on way more things more easily and is less situation dependent at what we
More general, you would say, yes. That is absolutely part of the reason. So thank you for that. And you also had one, I think?
Yeah, I wanted to say that you can just express your system in terms of generalized coordinates, and so you can
Okay.
like ignore all kinds of weird constraints that
Yes.
might make it hard to find equations of motion.
I very much agree. So I heard a couple of very good points, and all of them are true. So just very quickly to go through them. One of them is indeed that I haven't specified here in what coordinates exactly I am writing the Lagrangian. And I don't mean coordinates as in one reference frame to the next. I simply mean, say, polar coordinates versus Euclidean coordinates. Newton's second law is written in Euclidean coordinates. You are assuming that you write everything in x, y, and z directions. If you want to write this in terms of polar coordinates, angles, and distances, then the whole law itself changes. So that means that if you stumble across a situation, and this actually is your point, Ash, that if you stumble across a situation where polar coordinates happen to be preferable, for instance, you do gravity, use Newtonian gravity, then doing Newtonian gravity in x, y, and z coordinates is very crappy, right? The equation goes with 1 over r squared, and r squared is x squared plus y squared plus z squared. It's difficult. So that means it's much easier in r coordinates, because there's literally 1 r squared, makes a three-dimensional problem come out a one-dimensional problem. But that means that the whole rule doesn't work very well in polar coordinates. So if you want to use gravity and solve it by Newton's second law, you either have to write your force in terms of x, y, z coordinates, and then solve it as a three-dimensional system, or you want to solve everything in one r coordinate. That's much simpler because you have only one coordinate now, only r, but then this rule itself doesn't hold anymore. So you have situations, and this is your point, where one of them is better than the other. The nice thing about Lagrangian mechanics is that this rule is completely independent of how you've chosen your coordinates. It could be polar coordinates, it could be different reference frames, it could be anything. This rule is more than invariant. It's not just true in every reference system, it's also true in every choice of how you write your four-dimensional space-time. So it's much more general. That's one. Yes?
You say you can also use it in like quantum mechanics, the Lagrangian used in quantum mechanics, right?
Yes.
Well, that rule is kind of...
That is because of all the reasons that we're talking about right now. Because the second thing why this is preferable, it's a scalar. This thing is a vector, that's a vector. Lagrangian is just one number. So you don't have to worry about directions. And everybody who's ever solved a Newtonian physics problem where the one force in one direction influences the motion in the other direction knows that's a very difficult situation. Prime example, Lorentz force. How much a particle is moving in this direction through a magnetic field will make its force go in a perpendicular way, yes? So that means your x's and your y's get a very complicated system together. You don't have that in Lagrangian mechanics, it's just one number. Now, there's many more, but the most important thing is something we've already discussed. Noether's theorem. What does Noether's theorem tell you? That if you have a symmetry, you know exactly what numbers are conserved. The nice thing about Lagrangians is that once somebody gives you this L, doesn't matter where it comes from, whether you got it from Binas or some person on YouTube or just read a very complicated physics book. If you have a Lagrangian, you can immediately tell this number is conserved, that number is conserved, charge is conserved, that is not conserved, and that is not conserved. Just at one immediate glance. Now I challenge you to take this and prove the angular momentum is conserved, just based on this equation. It is. Planets have a fixed angular momentum. Mathematically proving that is very difficult. Here, if somebody gives me a Lagrangian, even if it's one I've never seen before, I can immediately tell this number is conserved, that number is conserved, that number is conserved, and that's it. That's Noether's theorem, of which I'm going to show you a mild version. Now, what I've talked to you about now is that what I want to do is replace our Newtonian physics by Lagrangian physics, and I hope I've convinced you that it's just as abstract. It's just one is one that you're used to and the other one is not. It has the same amount of information in there. The reason that we do this is because this comes with all kinds of benefits that the Newtonian one does not have. And yes, this is why in quantum mechanics and in quantum field theory, Jaco and such exclusively works with Lagrangians and never with anything else. Now, in the tutorial in a moment, I'm going to ask you to prove the following. This is just a statement in terms of words. The principle of minimal action chooses x and vt such that x is the smallest number. Okay, but what is that function then? How is x as a function of t? What is that function to make it smallest? It just says that it does. But how do you find that number? I will give you the solution. And the tutorial will prove that that is the case. So, let me first write it down for you. You take a Lagrangian, you take its derivative with respect to x, this unknown thing x, this unknown path. Some function will come out. What you then do is then you take your Lagrangian, take its derivative with respect to the v, which you also don't know. Of this derivative, you take the time derivative. Yes. I know what's coming, but go ahead.
Yeah, I've always wondered why does nature choose the path of minimal action and not of maximal action? Because just from a first derivative point of view, it shouldn't be able to differentiate between the minimum and the maximum.
I agree. And one of the exercises in the tutorial is going to be that the maximal action is also allowed. And I knew that this question was coming. So I'll leave that aside for a moment, and we will look at this during this tutorial. So, what does it say? It says that if I throw my pen around, and I know the Lagrangian for the situation, how much air friction there is, I know how much gravity there is. Somebody has given me that Lagrangian. Then I take the Lagrangian, I take the derivative with respect to x, take the derivative with respect to v, and of that thing I take the derivative with respect to t. Then I get an equation for x. X will drop out. Then this is the path that indeed makes this thing the smallest value, and hence this is what nature does. That's how it works. Abstract, yes? Again, it's not very different from Newtonian physics. Somebody tells you what f was, you have no idea where it came from. You put it in a rule, you have no idea where it came from. F is equals m times a. You solve the equation, and then you know how x moved, what x was as a function of time. Same series of steps. To finish for today, I promise you a mild version of Noether's theorem. So, by this you can calculate how things will move in nature. Following statement. Here, what is the energy of that thing? Now, Noether's theorem tells you what the energy is, and I'm just going to give it to you. take your Lagrangian, derivative with respect to v, multiply it with v, subtract the Lagrangian again. That sounds very randomly added together, yes? Claim. What you will get out is the energy of this system, this piece of nature. Secondly, this is conserved. That this energy will not change in time, whatever this piece of nature does. That's another exercise we'll do in the tutorial. But already, can you tell how you can prove this without doing the full calculation? What does it mean when I say that this number is conserved?
Oh, that the maximum. There's something to do with the maximum.
That is agreed. Your point, but phrased differently, how do you prove it in all cases? How do you prove that something has the biggest value? Or, excuse me, has a constant value?
Its derivative is 0.
Yeah.
Derivative is 0. What we'll do in the tutorial is the following. We're going to take dE dt, go through the calculation, you will always find that it is 0. That means energy is going to be conserved. Energy will not change. And, again, the tutorial will do this in full detail. This will be true regardless of L. Just the fact that L exists is enough to prove that this is true. Now, if I have not specified what piece of nature I'm looking at, I just say this thing describes nature, whatever that is, and you find that energy is conserved. What does it say about the statement energy is conserved? If I have not specified what piece of nature this is true, then it's just true for everything. Biology, physics, chemistry, biochemistry. This is the general proof of the conservation of energy. We have to go through it. It's a mathematical step. But can you already see what happens? You take this thing, take its derivative, blah, 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 blah. You get this thing out? That's something for the tutorial. Now, at this point, the only thing I've shown you is a different way to do mechanics. I've not specified, I need a couple of minutes more, but only a couple of minutes. I've not specified what piece of nature I'm looking at. That was good news, yes? That means whatever comes out is true for all. Now, if you look at this thing, is that invariant? It's a deep question. It's very important. If there's something going to pick up today, let it be this. Is this an invariant statement? S some number, is that number going to be the same for every inertial system?
No,
Why?
because the x and the v, the x function, for example, can change from one frame to another.
That is very correct. Because how much x a pen flies through space, because of Lorentz contraction and such, is going to be different for one observer to the next, and the v as well, because you know that you have this Einstein, there's the relativistic velocity addition rule. This is also not invariant, this not invariant, so you cannot expect this to be invariant. That's one thing. Second statement, how about dt? You have to integrate over time. That was your point, yeah?
So so you're going to integrate using the t, and then the t is going to be different.
Yeah, so that means that,
where you integrate.
I agree. I mean, dt, if it was Newtonian physics, dt is going to be the same number for all, yes?
Yeah.
But we are not in Newtonian physics, we are in a world where dt's themselves change from inertial frame to inertial frame. That still means that this number for this action, this s that comes out, is still 17 for one observer, but it might be 8 for another observer. It might even be that the maximum or the minimum amount that comes out for one observer is not the minimum amount for the other observer. Why is that a problem in relativity?
Why is that?
Because technically nature chooses the minimal action, and
Yes.
all observers should see the same path regardless of
Exactly. Now I'm going to repeat this because it's extremely important. Do you remember from our very first lecture that there were two postulates of relativity? One of them was either the speed of light is invariant or the Minkowski line element is invariant. Do you remember what the second statement was, the second postulate?
That the laws of physics
Are the
same
same
for all reference frames.
Exactly. The laws of physics, not the numbers that come out, but the laws should be the same formula for all observers. Now, this thing gives you laws of physics, right? You take this, do this step, that will give you the laws of physics. if the minimum of one observer is not the minimum for the other observer,
we have different laws.
you have different laws for different observers. So that gives us that second postulate that up to this point we have not used yet, is now we're going to use it. If you want to have your mechanics such that the laws are the same for all observers, there is something wrong at this point, yes? Can
so
you...
the thing about the inertial frame, like the fact that in inertial frame the type of x will be the same function, and in non-inertial one we can already see it, because when we try it we say, oh, if the object moves like spontaneously,
yes,
if there is a spontaneous like movement in a non-inertial thing, so the x will be different. So like probably the rules of physics stay the same if it's kind of an inertial frame, and if it's a different one then we'll have like different structures of like...
That's true, that's correct. In fact, you can already see the base to general relativity. What if you start to accelerate? Anyway, that's a long story. Main point, and then we'll go to the tutorial. The way that it stands right now, this thing gives you the laws of physics via this thing. But because you want the laws of physics to be the same for all observers with inertial frames, that means the way that it's written here as a non-invariant statement will not give you the same laws. That means we have to make it invariant. This we have to make invariant to be sure that whatever comes out is going to be invariant. Maybe you can already guess how to do this. No? Name me a couple of things that are invariant.
We talk about the P.
P is not invariant.
The formula.
This formula is invariant, that's true, sure. Anything else? But there's already energy there, we don't know what the energy is. This was the quick and dirty way. We cannot take the quick and dirty way. Name a couple of things that are invariant. Minkowski line element. What else? Speed of light. Anything else? Mass. There you go. We have 3 invariant things. So how about we make a Lagrangian just out of invariance, and instead of integrating over time, we integrate over proper time, because proper time is invariant. Then we have made by construction a Lagrangian or an action that is invariant, and therefore we uphold the law that everybody should get the same rules of physics. My claim, and again we will continue this next week, but my claim is that if you have M as an invariant, you have C as an invariant, and you have d tau as an invariant, there's only one way that you can build your Lagrangian that will be invariant and therefore will give you the laws of physics the same in all. Once we found that one, we go through the steps, calculate energies, we get all our relativistic mechanics. Okay, that's it. Let's go to tutorial in 20-30 minutes. Let's make it 30,
I
yeah?
understand about as much as I do.